So we continue our Princess Bride references, of course, in the class here. So this is to the pane and then interviewing a scientist. So first, we've got, as usual, some videos showing examples as part of our seeing variety, having ideas for your projects. So this group is trying to say, okay, if we want to understand what's going on in some kind of a simulation, from the point of view of a particle moving through this simulation, maybe what we can do is take the original path of the particle and then straighten it out, and then warp space around that along with that same transform to give kind of a particle eye view of what's happening through here. So you're saying, okay, I'm flying along, this thing comes to the right, then this thing comes from the left. Here's how the gradients move as I go forward. Here's the environment around me. But rather than doing it from the kind of 3D environment's point of view, you do it from the particle passing through there's point of view. And here they've, of course, got a line trace down the center showing what the variable density happens as it goes through.
What is this a picture of?
Yes, that was on
The curvilinear something.
curvilinear. So this is a particle path flowing through a flow field. I don't remember which particular flow field it was for this
Okay.
one. We can go back and look. Right, so this is what happens as it goes past a car, right?
Okay,
So on
that
top
I can follow.
is the streamline, right? And on the bottom is kind of what the car looks like from the point of view of the particle. And here is I'm flowing through a turbulent, simulation and trying to understand what happens for a streamline. And so this can simplify the very complicated geometry to just along the, kind of particular path that you're trying to understand, and you can see how changes in one variable affect others as you go along that particular path. So this is another example of picking the space in which you want to show your data, but here it's not just based on the grid, it's actually based on the kind of flow of visualization particle through it. This continues on our molecular visualization from last time. And this is saying, okay, instead of just showing the surface at one point in time of a molecule, this is saying, here's a molecular dynamics calculation, here's kind of how the molecule is moving around. Some parts move more, some parts move less, and they're basically showing you the solvent accessible surface of the molecule as it goes through the molecular dynamics, and then you can change the viewpoint while it's doing its dynamics to see what's going on. So this is not just the surface of the molecule as it's kind of in one particular configuration, but how much motion you expect to have on different places in the molecule. So you understand how often a hole would open up that a solvent could go in there, for example, and be acted on.
Why is there that hydrogen just hanging out in the middle of nowhere there? Oh,
This guy, yeah.
Oh, yeah, no, there's one there.
There's several of them. So these may be waters, solvent molecules. They may be hydrogens hanging out in the middle of nowhere.
Maybe they're just very weakly.
So the bonds are inferred based on distances, and so, yeah, they'll kind of appear and not appear. There. So this is looking at a vector field display, and it's basically taking a translucent stream, and instead of making it completely translucent so you can't really see the shape, it's actually putting a line contours on there so you can see how they deform over time and space as they go forward. So here it's got some transparency so you can see through the layers, but it's got opaque strips, right? And that's going to be a technique that we see over and over again for displaying things in 3D, is how can we set the transparency so you can see the object but also see the things beyond it. This is taking a transparent sheet at one time, one time across space, and showing how that deforms across time, right? So here the color is a nominal coloring. It's like kind of where I am in space, kind of the red is the little corner, the green's another corner, the yellow's the other corner. This gives you an idea of how it unfolds. Now this is completely transparent, and so it's not so easy to tell what the layers are, how much curvature there is, except at the silhouettes. But it gives you an idea, at least initially, of the deformation you see. And then they go on to talk about how they have to refine the meshes to kind of keep up with the resolution they need over time. All right. So cool pair of you tricks. This is something that's going to be useful for you there in class. If you press Control Spacebar, this brings up a filter search tool, and you can just start typing in the name of the filter that you want. So instead of filter as alphabetical, looking around this giant list, you can just start typing in, streamline or particle or surface or whatever you're looking for. If you have to do the same filter over and over again, the same set of 3 or 4 filters, you can actually define a custom filter and say, I want, here's the parameters to this custom filter, make me a custom filter, save it, reapply it later, reapply it later, reapply it later. And this saves you kind of from redoing a 5-step process over and over and over again. So remember, when you do your postings for the Homework 0, to make your posts private. That way other people can't see theirs before you turn those in, and then I'll make them public Thursday night, and you can start doing the comments. While you're reading Commonwear, pay attention to the guidelines. This is kind of the reason I went from the version 2 text to the version 3. He actually added these guidelines, and so he didn't want to do it because they're not like firm rules of you always do this, but it's very helpful when you're trying to think about this design. Why did I choose this? Or describe to me in the homeworks, why did you choose this? Or critique another classmate's homework and say, here's a principle that you should be using when you're making this choice, this design decision. It's a good way to think about kind of what is the reason that I'm making the decisions I'm making. All right. So this is a lecture that I added in 2008 to kind of drive home the idea of don't look only at techniques, but also how well they answer questions. And if I had enough time, I would make all the homeworks be basically, it'll give you an idea of the data set and questions. You'll pick a technique, and then you have to answer the questions using the technique that you picked, right? Because that would really drive home how easy or how hard it is to do these things. But I don't have that, so in the meantime, we've got a lecture on the topic. So basically, we talked about this before. The technique you choose hides and shows things, so you want to pick one that matches what it is you're trying to do. So, to the page. So here we go. This is a question for y'all. This is a data set mapped using the rainbow color map. One end is low and the other end is high. So tell me, not the features of the mapping, but by looking at this visualization, tell me what are the 5 interesting features that are present in this data. So for example, you might say, this is a temperature map, and so red is high temperature, blue is low temperature. Tell me what's going on in this data set.
There's spots.
All right.
Varying intensities that change as you go from left to right.
And what do spots mean in terms of the data?
Seems sinusoidal.
Yeah, but what does a spot mean?
Local maximum?
Uh-huh.
Minimum.
Okay. So values, local, min, and max. All right. And then you said this changes across the, is that right? Across the image.
Yeah, as you move from left to right, yeah.
Uh-huh.
Here you had it.
There's actually 2 sequences, right? Because the blue one goes to green, and the red one starts as green and then becomes red. So it's not like if blue turns into red. So
Okay.
2 separate, it's like 2 things doing like this kind of bit.
So I think there's a gradient from left to right, and then there's also a sinusoidal pattern drawn down.
Or some other discontinuity kind of thing, yeah.
Or just 2 intersections.
Yeah, I'm going with, and they both end up at the same.
All right, so when you say it's gradient left to right, do you mean that there's not 2 periodic sequences, that there's only a gradient in that, or
It seems like there might be, because it seems like left to right, it's increasing the entire time.
uh-huh.
And then top to bottom, you kind of go back and forth between rows.
Okay.
It's like a dampened, set of dampened sinusoids.
Yep, so it may be the same, may be different. Uh-huh, okay.
See, it looks linear to me, so I didn't think sinusoid. The color mapping probably.
See anything else?
I think they mean just in 3 days.
You seem to have this domain of all green. And
Uh-huh.
as sort of a,
The baseline.
yeah, sort of average value or
Uh-huh,
min max or something.
uh-huh.
You
Six
could be
answers,
looking into
2 of them
like a
correct so
V-shaped
far.
thing, you know?
Say again?
You could be looking into like a V-shaped thing and you're seeing
Yep.
different colors of light coming in from the two sides. It may actually be,
Anything else besides that main pattern that people see?
There's like, I don't know if it's it looks like there's a discontinuity at
Uh-huh.
a point. It's, sometimes when you're looking at a projector, it's hard to tell if it's something that's on the
And
screen.
it goes which direction? Vertical? Uh-huh.
It's like right in maybe the
2/3 of the way
fourth
across?
set of dots from the
Uh-huh.
right. It also looks like there's some sort of weird banding going on.
Uh-huh. Tell me more about that weird banding.
It looks like it might be concentric circles starting at the center.
Good. Starting in center. Sure,
Maybe.
okay?
That's just a guess.
Okay.
how much of this is optical illusion?
Well, we're about to find out. 1, 2, 3.
There do
4,
appear to
5,
be
6,
vertical
8. You're
stripes,
correct.
right?
All right, you
But
ready?
I'm trying to decide if they're,
This is the same data set, a little bit smaller, mapped to a height field, plus the black body radiation spectrum, and picking a viewpoint that's kind of angled down. All right, so it's the same data, instead of mapping it to a rainbow color map. Now, somebody can tell me what additional thing I did that I haven't talked about yet.
change the bloody colors all around.
Change the colors, yeah, and so basically, I'm here, the color map is not from Z, just absolute value of the thing, this is actually up from the local flat, right? So as you can see the slope there from left to right, and you can see that the ripples are the same, right? So you're correct, in fact, they were not two different periodic sequences, they were basically a gradient with the same periodic sequence both directions, yep. Now we can see that there's also a couple other of these discontinuities, right, that happen to be in green. And green happens to be a place in the rainbow color map where there's no variability that can be seen, yep. And the ripples are indeed concentric, but not from the middle, right? And so you can see that, you can get more, you can see the ripples because of the highlights much more easily. All right, so to make sure I wasn't cheating, this image is actually smaller than this image, right? It's got fewer pixels, so I haven't added more data here. And the one trick again is, coloring up from flat. So this is, again, when you think about how you want to display the data, what's the natural space here? The natural space to see the symmetry, which is what you would care about, is from the bottom of 3 of those, particular holes. All right?
What is that data set? Oh,
This is a data set that I made
okay.
to have kind of artifacts when shown with the rainbow color map, right? And so this is kind of a custom made just to fool you data set. All right, this is not a custom made, just to fool you data set. This, okay, well, the answer must be then that we're going to show everything as a height field, and that's going to make our life better. Okay, so this is a height field. So the question is, what are the shape of the small regions on this data set?
It's a projection of some kind of text if you look at it from above.
Yeah.
Yeah, it's small.
So here we go, if we map it to grayscale, right? And so this is a kind of, you take your coupon, and it turns out that the relative heights of these things were not so critical to understanding the text. And when you map, you get all of these high frequency things due to lighting and small subtle changes and kind of averaging that don't help you understand the data. Whereas the region, you can see much better. Here you can think about, we applied all of our luminance budget to seeing the region boundaries. And here we've moved a lot to seeing the shapes and the relative heights, which we didn't actually need to do to answer the particular question.
You can see some very interesting compression artifacts or printing
Yeah.
errors around the rural edges of the
Yep.
letters and stuff.
Yep.
So,
And so if
which
that
you
was what you're
couldn't
looking
see.
for, this
Yeah.
would be a good thing. But if you want to know the region shape, this is not how you want to use your coupons, yeah? Right. Okay. So that won't always be the case. All right, so I want to see here the distance between the two surfaces. And so one surface is an inside tumor surface, and the outside is a radiation isodose that was calculated. And we want to know kind of how far the isodose is from the inner tumor. On the left, we've made the outer surface translucent, uniform translucency. On the right, we've made it opaque. All right, and so on the right, you can kind of see the outside surface really well. On the left, you can kind of see the inside surface really well. Now you can see the silhouettes, right? And so if those happen to be co-located, which we don't know for sure, then it does give you a good idea of boundaries. All right. How do we start to make this a little bit easier? If you add kind of grown textures on the outer surface, now we can start to get some more shape information about the outer surface. It turns out that if you put them in motion, it helps a lot, all right? And so here, either if you do stereo or if you've got kind of motion, you can understand the shape better of these kind of multiple layered objects. On the left, we have the same translucent versus opaque, and you still can't see really what's going on kind of front to back. In the right one, you can, the speed of motion of the back object with respect to the front object gets you some idea of that, right? So the best motion, if you're going to do a motion, is either torsion pendulum, right? And so this is like the wedding clocks, right? So it goes and it comes to a stop at one end, it goes, it comes, because if you just do kind of a linear motion, you get this weird bouncing at the boundaries that make it hard to see what's going on. Or if you need to see the whole thing, then you can just spin it around, right? And so then you have kind of a looping. In either case, you can loop the movie and you can kind of see what's going on. Even better is head tracking, and so you change the viewpoint from where the head is going, and even better than that is head track stereo, right? And so if you can do those things, great. If you can't, at least think about, do I want to add some motion here to show these depth relationships in a way that's helpful? All right, so here is the hydrogen atom simulation of the electron density around that. And so here the questions are, is the volume density symmetric? And how does it vary near the value 17, right? And so this is basically an X-ray volume rendering projection of this molecule, and
17 what?
17, value 17. Yeah, don't know, no legend, okay. Even if there was a legend, it'd still be kind of hard to tell around where 17. So 17 is a certain level of grayness, right, in this image. All right, so we can make this a little bit easier if we take a surface, right, and that is at the value 17, right? And so this gives you an idea, okay, is there symmetry? All there is. It just didn't happen to be from this viewpoint looking so symmetric here because you were kind of passing through more or less materials, but there is a symmetry around another axis. That doesn't let you answer anything about how it varies around 17, right? So isosurfaces are very good at showing you the surface, but how it varies there you don't know. So this slice plane through, at least in this plane, gives you an idea of how much variation there is from one end to the other. This color map is mostly isoluminate, so it's going to have a hard time showing us details, but you know, it's at least giving you some idea. So this is a little bit better than that. All right, but now if we ask the question, where's the maximum value in the data set? You know, we would have a hard time with this version, and we have a hard time with this version, and so we might try this version. So this is a maximum intensity projection. So what's that mean? That means you look through the volume and you go along a ray, and whatever the brightest thing is, the highest density is, anywhere along that ray, you bring it to the front, right? And so the maximum cannot hide behind some lower valued thing. So the maximum here is, all right, so we know that the maximum is in one of these two rings, sorry, one of these two lobes, not inside the ring, but we don't have exactly a 3D coordinate for that. But okay, this is better at answering that question.
What is the donut, by the way?
The donut is, so there's like an s orbital and a p orbital.
It's a hydrogen.
But hydrogen only has one of those, and so don't know. See, you go beyond.
Any
The
chemists?
first question
You get
is
excited
something.
at the donut, right?
Yeah. Say again?
Can't get excited to other orbitals.
Yeah.
It's one.
Yeah. So I guess it spends most of his time in one of the orbitals, and a little bit of time in the other. Yeah. All right. All right. So this is, what is the microstructure inside of an organ, right? So here we've kind of shown you, here's, a liver, here's the backbone, here's some things, but what's the structure inside this? A little bit hard to tell. If you use a custom filter that actually is the tomato transfer function, that looks at local gradients. In other words, if you're looking down the viewing ray, how much is the density changing across my viewpoint? Gives you an idea of the local structure inside there, even for very small values and changes, right? So it's mostly the same value inside the liver, but by showing you the boundaries more strongly, you can kind of see this enhancement down here and some of the microstructure in there, right? So this looks like noise. In this case, it's structure. It doesn't help you understand the boundary of the liver as much as this does, but it gives you a better idea of the internal structure. All right. Which way is the flow going, right? So this is a technique that we'll talk about in the visualization, in the vector field visualization, which is blurring along lines of noise patterns, and so it's really good at showing high density information, except you got a 50-50 chance, right? It might be going in or it might be going out, you know, one of the two, right? And of course, you can help that by several different approaches, one of those being to animate, right? So here's an example of where you may want to have an animated visualization, even if the data sets you started with is static, right? Because it's showing you kind of how the flow would be happening, even at this instant in time in the vector field. All right, one of my favorites, I should say my least favorite visualizations, actually was published. So this is looking at where a balloon goes, right? So this is wind fields across, you know, I think maybe Europe. And so the legend is in the upper right corner. So the rainbow is used to show which direction the wind is blowing locally. And then the saturation, or kind of how bright the thing is, from black to white to bright, is showing you how fast the wind is going, right?
Fail?
And so, you know, where does my balloon go? So you start out here, and then you go look up in the map which direction it's going and guess how fast. And then you kind of integrate a step, and then you kind of go back, look in the table, figure out which direction it's going. And you hope you're not going in the blue direction or, you know, kind of the green direction, because it's really hard to tell the difference, all right? So, right, not recommended. So this is, you know, starting to kind of help that a little bit. This gets like, at least again, you know, you don't know which direction it went, but you have a 50-50 chance of knowing by tracing along one of these lines, and the balloon is going to, you know, if it started out here, it's going to end up here in this little vortex, or it's going to end up, you know, going off the image over there. Still don't know which direction. So this is Turk and Banks, did a lot of kind of work on this. So this is a case where there's, you know, arrows, and the arrows flow in the direction of that, but they curve as the airflow curves. And the size of the glyphs varies, so they're bigger where there's faster flow, and they're smaller where there's slower flow. And the density of them varies to be uniform across the entire image, right? So in this one, there were regions that were kind of more high density and regions that were more low density, although still pretty reasonable. Here, they try to show this what's going on, right? So if you have your balloon here, okay, you follow along these paths, and it shows you that you're going to end up right there, right? And so this is very, very good for answering that particular question compared to the other techniques that we have looked at. This has the deficit that you have to actually run a whole simulation on your data set to create arrows and remove arrows as the density is too high and too low, and locally move them around to make them evenly spaced. This also, I think, has the head-to-tail following rule, right? So if you look here, all these arrows kind of head-to-tail, head-to-tail. This is actually very useful for the way we perceive flow, because you can follow along the streamlines. If you randomly put them with the same density, it's actually not as easy to tell what's going on in the image. And so this is a lot of work to go into the visualization. You're not going to be able to just turn this on in pair view. Yeah, maybe we'll get you guys to work on that. But it gives you a really good understanding of what's going on. All right, so this is one of the projects that was in the visualization class, and the question was, how is PMCA laid out across the membrane of neurons, dendritic spines? All right, so PMCA is plasma membrane calcium ATPase. It's a thing that glows when there's calcium pumps going, right? And so this has to do with memory. So calcium seems to be involved in memory. We want to know how calcium is involved in the formation of memory. This is a dendrite. It's part of a neuron. This is a spine, a dendritic spine, and this will go up and attach to another neuron, and that's where they'll start to make connections about more memory form, less memory form, maybe to do with calcium. And so the question was, how are these two things related? So these are two 3D scalar fields, one how much PMCA, one how much DIO, and DIO is a membrane stain, so it shows you where the membrane of the neuron is, all right? So here was the way they did it, right? So this is slices going from the bottom up to the top, on DIO in the left, and then on PMCA in the middle. And so on the right, DIO is red and PMCA is green. So you're looking for places where the red happens to lie across the plane and stick out, and then seeing how much the green makes things yellow at those locations, and then trying to get an estimate across the whole 3D volume of how this works. Right? So you can see why they came and said, you know, can you help us with this? So the first two things we try were to throw them into pair view and have a look. And so on the left is basically isosurfaces, and so you see kind of the area where the red is high, the areas where the green is high. And as you spin around, the problem is there's so much green that it kind of blocks the view of the red, and you can't really get a good idea what's going on. The second one on the right is the maximum intensity projection, so kind of the brightest of those things comes forward, so nothing is occluded, but then you're very confused about what's in front and what's behind because things don't behave the way that they normally should. And so this is the traditional occlusion versus confusion trade-off we're going to have in terms of the volumetric data. And so after the course, they worked on the question of, okay, how can we do a little bit better than this? So this is saying, okay, let's take the surface of the dendrite and let's color that surface according to the amount of calcium that there is, right? And so here on the left is kind of the whole zoomed out view, and on the right is a zoomed in view around one of the dendrites. In this case, it happens to be that the calcium is higher around the neck of the dendrite than at other locations, right? But the scientists also wanted to know kind of where is within the spine the greatest concentration, right? And so the question was, what is the technique that shows both this and that? And after much careful thought and consideration, the answer is kind of there really isn't one that shows both of those. And so there's this tool that you can put in that is a slice plane. And if you position that in the middle of that spine, then it extracts out for you what the data looks like in that 2D slice through the middle of the spine, right? So this is saying, okay, let me study this spine, but I want to see inside and see what's going on. It turns out that right down the middle is the highest value of that. Now this is a little interesting because in the left, geometry is showing the membrane and color is showing the amount of calcium. But in the right, color is showing the boundaries of the membrane, and height is showing the concentration of calcium, right? So you need to explain to the scientists why we switch these things. And the answer is because it turns out to be much easier to understand relative concentrations when they're mapped to height than when they're mapped to a color map, right? So that we're going to learn on Thursday or next Tuesday that there is no interval color map that can kind of show you all the things you want to see at high field as you can. And so how you want to answer the question will affect how you map your data sets. Different questions will get different mappings. All right. And then the next question that scientists always ask is, that's really cool, can you give me the numbers back out, please, right? And so in this case, if you go actually build a tool for science, they want to know, okay, can I put a spline down here, down the center? This is spine spline, right? Spine spline, right? And then pull out the two concentrations. And we'll learn later in the class that blue is never a good idea for displaying on black because the luminous contrast is not there. And so they chose a poor color for one of those two displays, but did well on the other thing. So we'll give them a little slack. All right. And so this is obviously meant to convince you that choice of technique matters, and you should be thinking about that not from the point of view of what's cool, but what's useful. Some things jump out. Sometimes they're unexpected, right? Oh, what the heck is going on with those ripples that are in the center of my, display there? Some are found if you look. So maybe, if you have a secondary question, you may get away with using one display to answer both questions if one's more important and the other's less important, right? So you can do a color map that uses isoluminated colors. It doesn't answer the second question as well, but doesn't hide the shape. And then, there's no single technique is going to let you answer all these things. And so then you want to add multiple display techniques. And the one danger here is, you saw that there was, three of the things that we saw clearly in the data set from the made up data set were incorrect. And they were put there by the way the rainbow color map maps things. And so we want to be making sure that that doesn't happen. The green banding area is very clear, noticeable, but it's in the data, it's in the color map, not in the data. All right. So a second topic for today is to kind of start talking about how to interview a scientist. If you are a scientist, this is like you're going to now be trained in doing visualization, and your friend in another domain asks you how to use visualization. You're still going to have to interview a scientist, and they're not going to be speaking your same language. So this actually turns out to work pretty well for both computer scientists and domain scientists. So in this class, I'm doing this right now. I'm going around interviewing scientists, coming up with question sets for the homeworks, and then you're going to do this as a group during the second half of the semester after the spring break, where you kind of do a second round of design, dig out a couple more questions that they came up with because they saw the visualizations they've got for the homeworks, and be making this work. So I kind of want to walk you through what this looks like. So there's two things you want to have an outcome from a meeting with a scientist. One is what scientific question that they're trying to answer, right? Their goals in their terms for what they want to know. So this is basically not about anything necessarily visual, but really I'm trying to understand how calcium affects memory formation, right? So how is PMCA laid out with respect to the dendritic spines? Very specific questions if you can, and this helps you guide the selection of the visualization technique, right? So you can say, okay, well this technique or this technique better help them answer that question. If it's I want to see what's going on here, I don't know which technique is going to work better because I don't know what you're looking for. But if I do know that you're looking for correlations between these two fields, now I can start to understand which technique would be better for doing it. The second outcome is to get a description of and a copy of the data set, right? So how was the data collected? How many data sets were they? The type of each? Are they scalar fields, vector fields? If they're scalar fields, are they nominal? Are they interval? Are they ordinal? You know, all this. And then get the data set, so it lets you start getting into the visualization code, right? And so almost always the case, the scientists will say, oh, I've got something now, but next week I'm going to have a way better, visuals, I'm going to way better data set, I'm going to clean it up, I'm going to have a bigger one, I'm going to have better simulations. Oh, next month I'm going to have this great thing. And the key is to say, okay, but I just want to load it into my program, right? Right? And so there's this whole pile of work I have to do just to get it into my visualization program. As long as the format of the data doesn't change, I don't care if it's blank, right? I just need to know, can I load it in, can I see anything useful? Okay, great. It doesn't have to be the world's best data, it just needs to be some data. And then you need to make sure that you don't try to publish that before checking with them, okay, is it okay if I use this as an example? No, that was the horrible data set that no one should see, right? Here, let me give you another one to put into the paper. All right. So what makes a scientific question a good question? So it describes a goal that the scientist has in understanding the data better, and it's either in their domain language, which you learn enough to figure out what they mean by that, right? Or it's in a generic task language, right? And so we're going to be learning a generic task language. We've already done that last class, which is, okay, it's scalar fields. We want to look for correlations, relationships between 2D scalar fields, right? And so it may be faster to teach them what a volumetric scalar field is and what maximum and minimum are, have the conversation in a task-independent domain, than it is for you to learn the terms that they have. But it may be easier for you to learn their terms. Either one is okay. It's a specific goal that they have. And it's not focused on techniques, right? It's not use volume rendering for this, or show me a color map of that. It's, I want to understand the relationship between these two variables. I want to see the relative heights of local maxima on this data set. I want to see, so forth. And again, it's specific enough to guide a selection between two techniques, right? So how would I know which one is better? It helps better answer this question. All right, so here's some example questions. And so the poor questions here were actually turned in as first drafts by students who had this lecture ahead of time, so pay more attention than they paid. And so the better questions are the ones that they ended up with after a few iterations, right? And so one of the first things you're going to do in the design project, the second half of the course, is turn in a goals and data sets description written down, because if you don't get good sets of questions, you're not going to have a good outcome in your design, right? And so we actually iterate on the questions a couple times to make sure that they make sense before you go forward. So on top, right, so using volume rendering techniques to visualize tumor tissues, right? So it's vague, and it focuses on a technique. It's trivially satisfied. I use volume rendering technique, therefore it is better than others, but it doesn't tell you anything about how it answers questions about the data. Evaluating tumor location algorithms in 2D MRI images. Okay, this is better. It has to do with asking questions, but the evaluation is vague enough that you couldn't know, well, did you want a maximum min comparison? Did you want a difference comparison? Did you want a correlation comparison? 3 techniques would help to answer that. Use multiple variable display techniques and marching squares algorithm to visualize areas with abnormal grayscale values in 2D MR slices, right? Again, this is telling you how to do some implementation, but it doesn't tell you, what are you trying to learn, right? So you couldn't find it. So better questions. Compare the surface predicted by our tumor detection algorithm to 5 MR volume scalar fields. Where does it overestimate and where does it underestimate, right? Okay, so now you can say, okay, where can I see the tumor algorithm gets it right? Where does it get it wrong? Where is it kind of on the outside? Where is it on the inside? Now I can start to evaluate techniques, maybe slicing techniques, probably not the simple transparency techniques that we just saw in the example, maybe some with kind of strokes on top of it. Understand the relationship between 5 hand-selected tumor surfaces drawn by different radiologists, where they're the same and how different are they when they differ, right? This is something I didn't want to know, right? When the radiologist who's going to do surgery on you segments the tumor, and then she goes back in an hour and segments the same tumor again, she doesn't get the same answer, right? Liz Bullitt. She's like, well, I get different answers. And so she's like, I want to know, where am I confident that I know the answer, and where am I not confident that I know the answer? And so they wanted to know. So most surgeons will say, no, I want to know where to cut, right? And you're like, well, I can't tell you, it's big. She wanted to know, no, I want to know where we have some margin, where we don't know exactly where the edge is, so I can take more margin out there, and so forth. And so, yeah. All right. Oh, the room is going to shut down again. Okay. So some potential problems, right? So you go in to talk to somebody in another discipline, and how do you talk to them and understand what they're saying, right? And so first you need to understand the science that they're doing, right? At least an overview. What's the basic idea that you're trying to do? Trying to understand how the distribution of stars are in our Milky Way galaxy, and what mixture model in the universe kind of predicts accurately that. And you're going to have to keep asking questions until you understand, because you're like, what's a mixture model, right? And I'm going to show you an example of that at the end of class, what that might look like. But the important part here is that you don't feel that you're stupid, right? Because you go in, this person has all this jargon, has all this scientific sophistication. You're not stupid, you're ignorant, right? Ignorance can be fixed. It just means I don't know something. You can ask questions until you do learn that something. And I've been surprised by how actually willing and eager most scientists are to explain, and they have struggled to do it sometimes in plain language. I have some of them say to me, oh, I've never had to explain this without my jargon before, but they're interested and willing to do that, right? And then you learn something about it and you just, all right. There's going to be a couple things. One is strange nouns and acronyms, PMCA, DIO. Mostly you can just get away with learning what these are and feeding back the right one with the right data set, right? And then they're happy, right? This is something, it's got a name, here's the name, great. You want to know how DIO relates to PMCA. I'll show you that, that'll be fun. Then there are some basically deep questions that you need to understand what's going on. If you understand quark, gluon, plasma, quark and gluon may be a name, but a plasma you better understand what's going on. Right? Display that. All right. The data, geometry, and tasks may be a common language. So again, if it's, you may some part be in the domain science language, but you may also be talking, okay, a scalar field is just a value to place in space. I think these are all scalar fields. Yeah, yeah. You want to see the relationship between these two scalar fields. Yeah, yeah. Sometimes that can be a way to go. So there's also a fear on their part that you don't share their goals, right? They may think, oh, you just want to make pretty pictures, right? So one of my best collaborators for the last 15 years has been Rich Superfine. And I had an undergrad student that worked with him. I said, well, tell him we have this VR interface to scanning probe microscopes. Yeah, I understand my data. I don't want to see the pretty pictures, right? And then he comes over, he tries it out. Oh my gosh. If you learn something about your data, then all of a sudden you're hooked. Can I have it by yesterday? And all sorts of things happen. But there's a natural fear, because a lot of people try to make pretty cover pictures, that graphics and visualization is just about pretty art to kind of, be excited. And the answer is no, I really want to help you answer your questions, right? And if you start asking questions about what are your goals, what are you trying to answer, that will help allay their fears, right? Because you really do care about what is it you're trying to do, not how do I make a pretty picture to show you what's going on. The second is, of course, you make those fears unfounded by your actions in the semester. You actually do designs that are useful rather than beautiful. And then the next round of students has an easier time talking to the scientists. All right. A couple of other potential problems that have come up. One is, they may think it's impossible to do what they actually want, and so they won't even ask. And it turns out that you can ask some probing questions. Well, would you like to know how this correlates to that? Would you like to know how this, oh, well, I didn't even think that we could answer that question. Okay, well, let's, see about doing that. Not promising that we can, but at least I want to know what it is that you would do that. Sometimes they're too high, right? They'll ask for these easy to state things that are impossible to implement, right? I just want a real-time Fourier filtered transform of a 3D volumetric data set shown with 5 things that will grow, right? Okay. There's computational and perceptual reasons why we can't do that, but I understand it's easy to ask. Okay. And the other is that they may be different than visualization. And so I've tried to screen that out in terms of the class, but as you talk to somebody, they'll sometimes be looking for image analysis, right? I want to put in my images and I want a number out, right? I want to put in my images and I want kind of a 2-dimensional vector of how likely it is that this happens or not diseased, which visualization is not going to really help you do. Visualization would help you come up with an algorithm you might apply to images and kind of see what things you should look for, but it's not going to be something I'm teaching you about in class. So I have him go talk to Mark Needhammer, and he's doing a class on image analysis, and then it works fine that way. So the other thing is that they'll know techniques that they kind of have seen and they want to try, right? And so they're really smart people. They know what they're looking for, which is a really big help to us. Out of their field, they'll often think conservatively, right? If you could just change the color map on this to be a little bit, more useful, or if we could do 2 slices instead of 1 slice, rather than, oh, by the way, we can just draw you the surface of this and color it by the, whoa, I had no idea you could do this, right? And so you should listen to what they're saying, because that may tell you what they want to learn. And then you tease out the question. Oh, if you did displayed that, would that be answering this question? Yes, it would. Okay, good. Well, let's think about how that would be, right? And so during the class, you're going to see all these different examples and say, okay, which is the possible, of all things that we know, is the best one to apply, which may be the one that they thought of, but it may be something completely different. All right. So again, you can try to look for common task language, right? Understand the spatial overlap between 2 or more volume scalar fields, right? So that is kind of the one of my tumor estimation algorithm is one thing, and the actual tumor is another. I want to see how they relate to each other. That's really understanding the spatial overlap between 2 or more fields. Understand shape and size of a feature present in the 2D scalar field, right? So I want to find the mounds or the divots or the kind of ridges. I want to see what's going on in the shapes. Understanding relationships between a volume scalar field and a volume vector field, right? So how is airflow impacting temperature? How is temperature impacting airflow? Right? And so you may be able to kind of back away. Now, it's useful to you, at least, to do this translation internally, because then that gives you access to, okay, what techniques are good for that? You don't have to ask what techniques are good for showing kind of trout, migration patterns against, fluid. No, I want to understand particle traces against volume, vector fields. All right. But it also is another way to kind of do active listening. Those of you not encountered active listening is when you're listening to somebody, you're not, as I normally am, coming up with a counter argument that I want to make to the thing that they're saying and I can't quite hear because I'm coming up with a counter argument. I'm listening to what they say. I repeat back to them what I think I heard them say, and then they can say yes or no, you got something wrong. So this is a way of active, so I think of flow air as a vector field, right? And I think of temperature as a scalar field, and you're asking a relationship between the vector field and the scalar field. And they'll be like, yes, no, or I don't understand what the heck you're talking about with vector scalar fields, in which case you say, okay, I want to think you understand the airflow compared to the temperature. All right. So it turns out that I've mentioned this before, that iterating the design really is important. You can't get there in the first step. Don't be disappointed when you realize that you've kind of done all this work, you came up with the visualization, and they say, wow, that's really cool, but now I want to learn this. Well, why didn't you ask for that in the first place, right? Well, because I didn't know you could ask for that in the first place. So this is, Linda Chin, who was the keynote at the BioViz conference, talks about this, right? You need to sit down and iterate on solutions, right? And they'll see what's possible. You'll see what they really want to learn. Actually, sitting with them in the lab can show you that they're asking questions they didn't kind of describe, because again, they may not have thought to ask for that. And most of the findings from the HIT-C tool came from sitting them, watching them use the tool, realizing the new things that they were trying to do with the tool, adding those in kind of as semi-automatic techniques. The rule bender and the visualization embryonic development, these were, again, papers that were there at the conference, and kind of group after group was reporting. He's sitting next to the scientists, seeing what they're doing behind the scenes. And so I ran, for a number of years, the visualization contest, and we're going to use the visualization contest as one of the homeworks in this class and one of the potential projects. It's basically taking these rules and lobbing a set of data set and questions over to the visualization people, and they give an answer, and, ta-da. So that is kind of the first salvo in a long conversation, right? So last year's conference contest, the winner actually is picking as his dissertation topic that problem, who he never would have encountered with. And so then they'll do a couple more rounds, iteration on the dissertation topic in that. But it's a good way of getting data sets out there that are better than us as visualization folks drawing spheres and collections of spheres and the bunny and the, my brain that I happen to have scanned, but actually things that people care about, of course. All right. So, man, I'm talking too fast today, so we're going to end
As
early.
opposed to,
I was talking this fast before, too?
you talk pretty fast.
Yeah.
And I talk really fast. So.
Yeah. So when I talk too fast, somebody's got to slow me down. Sorry. I get excited and I go. All right. So now we're going to do an interviewing example of what it is like to interview a scientist. I'm going to be the scientist, and I'm going to be the interview person, and you guys get to pick the topic. Here's the two topics.
Well, let's do particle collisions.
I know what that means at least.
All right. Okay,
sort of,
so this is,
in more respect to fixed cost.
I work with Stefan Bass at the camera. The other cameraman.
Huh?
The other cameraman.
Oh!
Sorry, I was too busy listening.
With Stefan Bass at Duke University and Scott Pratt at Michigan State. And so Stefan was the one, and his students, Hannah Peterson was a student and a postdoc that we interviewed about this. And so that'll be kind of scientist. So when I'm facing this way, I'm the scientist. And then when I'm facing this way, I'm the visualization person. I used to put a hat on and off, but that just got ridiculous. All right, so let me reload this into my head. All right, sorry. Hi, I'm here to talk with you about your data set and how we might visualize what's going on. Great. We're looking at relativistic QGP and it's understanding its materials of state. Okay. Sorry, equations of state. Okay, so equation of state is probably not some rule that the government has to abide by. And what is QGP? Oh, right. So QGP is quark gluon plasma. All right, quark.
You're facing the wrong way.
Yeah, I'm me writing back. Gluon. This slows them down if you can start writing things down. Right?
So bring a whiteboard with you.
Right.
Yeah.
So one pen color is for data sets. One pen color is for questions, right? One pen color is for other things, right? Because then when you take a picture of the board, you can remember what the heck is going on with this. All right. Quark gluon plasma. I think I've heard of quarks and gluons. Right. So quarks and gluons are the fundamental particles that make up hadrons. And so there's 3 quarks in a proton, and there's 3 quarks in the neutron, and the gluons hold those together. Okay? Tell me about the plasma. So if you take 2 sets of 27 gold nuclei, and you collide them at 99.99999, the speed of light, it heats up so much that the quarks and the gluons dissociate, and they form just a liquid, a fluid, a plasma with quarks and gluons in there, and that's the liquid phase. Okay? And so what we're doing is trying to understand the equations of state and how the behavior of this system moves forward in time. All right, so tell me again about the equation of state. So the equation of state is the, how would you explain it? Is the del this grad that equals to something, something, something. All right, so this is like how the particles interact with each other and the equations that heat turns into motion and pressure and things. Yes, exactly. All right, great. And so these are all variables that you have inside. Can you kind of list some of the variables that are in the equation of state? And he'll list 5 or 6 random things. Okay, so I heard you say velocity. Right, there's transverse velocity and then there's z. Okay, so what is z? Z is a relativistic velocity in the frame of reference of the collision. Okay, and that's somehow different than the other channels? Yes, it turns out that its time is compressed in that axis, and so we think about it that way. All right, so do you want to think about this as like a 2-dimensional thing and a 1-dimensional thing, or somehow scale that to match? Oh, actually, we can do the TZ, which is the time relativistic scaling of that, and that produces a 3D coordinate system. All right, so I would think about this as a 3D vector field of just things moving around. Yes, all right. Right. And then you make yourself a note that 1 relativistic. And then you hope that doesn't matter later, but maybe it does. All
You've
right.
got 2 time bases. You've got regular time and then the relativistic time. Because the data
It's,
points have like timestamps on them, right?
Yeah. Yep. So they.
I guess time is time,
The
right?
yeah, the time is time. There's one time. It's just that it's moving so much faster in this space that you actually have to take into account the relativistic velocity if you want to understand what the 3D thing of this thing that explodes at the speed of light.
It's quantum stuff.
Yeah.
And don't even get him started on the color quantum charge things. Yeah, I did. It was scary.
Depends what preference, right?
All right. Okay, and so
Yeah.
tell me kind of what questions you have about this display. All right, so we're trying to compare against experiments that are done at the LHC to look at the particles that come out and they hit different detectors. And we're looking at the histograms of the frequencies and the energies of these particles, and we want to see how those compare to the simulations. Okay, but in the flow here, there aren't any particles, right? So gluons don't come out. He says, right, and so what happens is there's a cooling phase. As this cools down, that emits particles, and they go into detectors, and we can compare it against each other. Okay, so then there's going to be some other part of the simulation that turns this into particles coming out, and then the simulation to detectors going over here. Yes, exactly. But we're not actually going to talk about that in terms of this question. What we really don't understand is the behavior of this quark gluon plasma. They'll just go off on these tangents, right? Okay. Oh, okay. So tell me the questions you have about the quark gluon plasma. What is it you want to understand here? Right. So we want to understand. What other questions do they want to ask about this? It's been 4 years now. Okay. So we're looking at kind of the relative densities of quarks and gluons. So density of quarks. All right, and we're trying to understand how kind of behavior of one affects the impact of the other. All right, velocity, Q, G, impact. All right, so do you mean like how the velocity of one affects the velocity of the other, or how the velocity of one affects the density of the other, or how the density of the one affects the velocity of the other? Actually, a lot of this has to do with temperature and with pressure, and understanding how these kind of motions cause increases in pressure, which then cause things to flow apart, which then cool and then kind of
Coalesce?
condense into particles. All right, so there's some more data sets. There's pressure. And there's temperature. And it's pretty normal to kind of bounce back and forth between questions and data sets and questions and data sets as the whole time goes on. Okay, and so you want to understand and there's densities of quarks, density of gluon, right? Okay, and so you might want to understand how pressure interacts with velocity, or you might want to understand how density impacts temperature. You might want to understand how, and this would have been a whole kind of back and forth conversation, how pressure, in other words, pressure drives temperature, or vice versa. All right? And so it's kind of back and forth, trying to define terms, asking questions, getting answers, trying to nail down questions. And some of these, they'll just say, no, I'm not interested in that at all, right? And that's okay. And then at the end, you'll have a list of questions, a list of data sets, ask about, can I get some of these data sets and how I might load them in? Are these time series? Is there missing data? What's the lattice the simulation is run on? And then you'll ask them to rank the questions, right? And so you say, okay, I'll give you 10 points. Allocate them. If you want 100 points, take 100 points. Right? Allocate them any way you like, right? And so they might say, 95 is what I care about, this, and 5 is this, and that's it, right? And so sometimes they'll say, 60, 10, 10, 10, 10, right? And so this kind of, as you're doing your visualization design, lets you know which things you want to make sure you display most effectively, and then which things you might just try to add on as secondary displays, or if there's two giant questions that they care about, you might do two designs, one to answer this question, one to answer that question. And so this will help you kind of get at that answer. So there'll be, again, terms that you need to know, But then terms you need to break down, like equation of state, we turned out we needed to understand what that was, because that was the raw data sets that we were looking at, and these were the data sets they care about. The other one he'll talk about is eccentricity, which took me a long time to figure out what the heck he was talking about. Eccentricity, they talk about in terms of the simulation, but what they really mean is how not straight on were the collisions, right? And if the collisions are not straight on, if the collisions are straight on, you get this sphere. If they're not straight on, you get this ellipsoid. That's kind of the slab where they hit each other, and it's thinner in two directions and fatter in one direction. And they talk about the eccentricity of the resulting thing, but it's resulting from the eccentricity, which means it's not lined up in this.
Eccentricity?
Eccentricity.
Like eccentric?
Eccentric, yeah.
Okay.
Yep. Yeah, not having to do with
Not
egg
eccentric.
centers,
I was
right?
like, what?
Yolks, what's it got to do with yolks?
The yolk's on you. Yeah.
And so, so there'll be some terms, it'll take you 3 or 4 going around to figure out what are they talking about that. And it really has to do with, in that case, something about the experiment that they actually don't know the answer for a given experiment because the thing is so small they can't possibly tell what's going on. But they infer it by seeing the behavior, and then they group them after the fact according to this outputs into how it probably was in eccentricity, and then they look at kind of how eccentric ones are compared to head-on collisions, right? So that would be another question that we teed out of them during the question that they never originally asked was, actually we want to compare 2 of these simulations, and we want to see how this simulation compares to that simulation, not in detail, this is exactly what happened to every coordinate, but in kind of overall shape of how these 2 things are different, where they're the same.
Was that actually the question they wanted answered?
That was among the questions that they wanted answered. There were probably 12 questions that we came up with for this whole thing. Some of them actually were to do with these distribution of particles. And so they do this simulation, and they do a cooling simulation. The particles go into simulated detectors, and they get histograms that look like this. And they want to say, okay, how does it change in the equation of state? How do changes in the sensor kind of estimates? How do changes in the eccentricity map to different things over here? And they want to look at ensemble runs. So they want to do like 1,000 runs with different settings, and they want to understand, which, in this 5, 6 dimensional space of possible universe behaviors, which ones best map to the ones that we see in the actual universe. And so we've gotten up to 5 display things, and then Femi's, Alabi is working on the question of how do we statistically go from the 1,000 simulations into clustering in high dimensional space, and then show you the kind of behaviors that you get, so you know which cluster is probably right, and then how do you show the variation within that cluster to see what's going on. Because there's no way we're going to draw visually 1,000 things that you're going to see, right? We can get to about 5, and we're kind of out of visual channel for what's going on. All right. That's kind of an example of how a thing might go. All right, we get done early today, which is good because I've got to talk to somebody about a data set. It's possible for, there we go. Good. So Thursday, we're going to start in on 2D color maps and how color can be used to show data and not. And then next Tuesday is expanding that to all the different 2D scalar visualization techniques. And then we'll have a week and a half from then will be the first homework, which will be applying those 2D scalar visualization techniques on homeworks to see which ones work out better and which ones don't work out. We'll answer those questions. All right, see you then. Thursday, homework is due by midnight, so upload your private posts.